It is, as its name suggests, an umbrella that doesn't rely on traditional materials to keep them dry, but instead creates a force of air which is so strong
What this
it actually
conversation? I
deflects
can't
the rain
believe
away
it.
from the area above you. And
I think it's
talking of
good.
that, you might want to take a look at this. Because watching a hawk take on a drone for invading its airspace never gets old.
But you saw
And for more of that kind of stuff, go to bbc.com/click.
the air umbrella. No. What do I want to look at?
The air umbrella, like a Kickstarter that never got made.
Don't know. I never got one myself, so.
Mythbusters tried to build one and said it was impossible.
Is that right? That'd be a good question
He said like
to do in class.
the rate is actually falling, like in order to get the amount of air pressure needed to actually
Out of Northern California,
it would just completely, like, you wouldn't be able to have it as a handheld.
Well, it would balance, right? So there's enough stuff pushing out each way that it wouldn't.
Dozens of homes destroyed after a huge explosion last night. It was apparently caused by a broken gas line. It happened in a San Francisco.
You could work out the force that you'd need to be able to move a raindrop.
International
Right?
Airport. Priya David Clemens is at the scene in San Bruno this morning with the latest. Priya, good morning.
Erica, good morning to you. We're right at the edge of where the fire started.
Well, we don't want to talk too much about death and destruction, but we're talking about pipes today, so maybe run this down. So we're talking about pipe flow. What I think we'll do today is kind of recap something from week 8, conservation of energy, which we're using now. We'll talk about dimensional analysis, which was week 9. You might be reviewing the things as we speak to understand that. And then we'll move more into pipe flow. But to put it in context, pipes in houses, not so interesting perhaps, but of course the lifeblood of how we run our lives is energy. Energy is supplied by fuels and energy carriers. Fuels would be natural gas. And of course, I don't know, maybe if you remember when I sent you back to week 1.2, the very introduction would have talked about all different applications of fluid mechanics. One of them would have shown a network of pipelines in the US carrying gas, natural gas, up from the Gulf, it used to be, to the northeast. Now from the Marcellus into trunks that would take it also across the northeast. In northern Pennsylvania and southern New York, there are salts. And there are underground storage caverns, which are developed just by drilling a borehole down with casing, circulating water at the base of that casing, and bringing it back up with solution with dissolved salt in it, and then slowly retracting the casing. So you get maybe 1,000-foot tall cigar-shaped cavern, which you can then just pump natural gas into. And when you need it, you pump brine in to displace it. It goes to New York City for everyone to start up their days at 7 o'clock in the morning, and in their evenings at 6 o'clock in the evening. And it allows you to have storage within a system to be able to supply it very quickly to that location. So pipes are a common way of moving things around. Of course, sometimes things go wrong. I'm not sure why we're concentrating so much on San Francisco Airport. San Bruno is very close by, and this is just a ruptured pipe in a neighborhood that was a problem. I'm not sure that there are casualties. And so the other, okay. So the other way to transport fuels.
On July 5th, 2013, at about 10:50 p.m.
2013, 12 years ago. I guess this is it. I won't show all of this, but this is actually a tragedy. So the other alternative to being able to carry things around, such as oil in pipelines, is to transport it by rail. We've talked about rail cars already when we talked about accelerating fluid. We mentioned that these black rail cars are kind of flared, go up at the ends to be able to accommodate accelerating fluid when it pushes to the back of the tanker. And so that's a common way of, for instance, getting oil from the Bakken in North Dakota, which is very volatile crude, I understand. and transporting it by rail across country. So this is somewhere in Quebec, Lac Mégantic, big lake, or magnificent lake, I don't know, not magnifique. And it was transported and left overnight outside a town with the engineer of the train putting the brakes on the locomotives to leave it for the evening, and tested the brakes, the solid brakes, to make sure they were on, and apparently they were, but also there were some air brakes which were contributing to that static holding of the train in place. And unfortunately, overnight there was a fire in the train. The local fire department came out to put it out. They put it out, but they also turned off the, you see trucks on the road, people sleeping in trucks overnight, they leave their diesel motors on, same deal here, they shut it off. And in shutting it off, they shut off the air brake part, so no longer was it held. And at some time, so the red must be the solid brake, the yellow must be the air brake that went off, the bar is the threshold for when it starts moving. This was an inquiry after this incident, this tragic incident, and as a result of that, once it hasn't got enough resistance to be able to stop it moving, then it starts moving. And so it rolled down, unfortunately, into the town of Lac Mégantic, chug, 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 and derailed. And I think I was listening to last night, 47 people were killed just as a result of that, maybe 12 years ago. And so pipes blowing up in San Bruno is one thing, but that risk that you take avoids having to transport it in different ways. I also remember that there was a plan at some stage to get natural gas pipeline. It was supposed to come along Burroughs Road in State College. And I think all of the people resented that and opposed it. And the university had to bring it in. When the university changed from burning coal, they burn natural gas now in the steam plant, which is on the corner of Burroughs and College. And there's also a plant on the other side of campus as well. The one on College and Burroughs used to burn coal, but converted now to natural gas, and that gas has to come in somewhere. It now comes across campus rather than through the town, which was cheaper, but not ratified really by the residents. Okay, so that's kind of pipe. I guess that's a diversion from pipe flow rather than anything else. We had the umbrella. I guess the other things going on, of course, is storms. Got some stuff in the news today. What is she called? Is it Melissa? It's an M, and a lady's name. So is it Melissa? Yeah. And so interesting things related to that. So a storm surge of 13 feet expected. You can calculate whether that storm surge is due to just the barometric pressure. Actually, it might be fun to do it. So why not? Oops, didn't do that. Right. So, Melissa, what do we know about storms before we get going? I guess we don't have any space. So, tests. Anything, feedback? Doing well, I think. Right on par, I think. The next one, I posted the material yesterday. And maybe as we talk today, we'll go back. It'll cover 8, 9, 10, and 11 weeks. So 8 is energy equation, upstream to downstream with energy losses. 9 is dimensional analysis, which we'll use today. And 10 and 11 are pipe flow. So we'll talk briefly about that. But if, I guess, what do you know about storms? Not bad. So you know that storms rotate counterclockwise in the north and actually that's the same direction, isn't it? So get rid of that. The opposite direction so counterclockwise in opposite directions. That's a fluid mechanics problem, of course, as well, right? Because if you think about the velocity that the Earth is going around, this would be V1 and V2. if you think about that for the plan view of the cyclone, then if this is going at V1, and if this is going at V2, we know this, right? Because if you wake up in the morning, the sun starts going westwards, waking up California 3 hours later. And so the sun doesn't move, so the globe has to be moving in this direction. And it has to be dragging on the bottom of the air mass which is above it. And so if you think about what's going on, is that you could imagine that if you draw a line exactly halfway between this, then you could imagine that this vector plus this vector gives you V2, and this vector plus this vector gives you V1. And so you could think of this as just an air mass which is being moved by this and this. So this is this excess component here. This is this excess component here. I've just drawn this line halfway between the difference between these. And so that's why you get the rotation. So it's just by the fact that you have underneath the air mass, you have Newton's law of viscosity. It would be dV dt. So if you looked at a column versus horizontal, you'd know that the distribution, not very good, be doing something like this. This would be moving at the velocity of the Earth attached to it. So this would be, if you want to call it this, delta V and delta V, they're the same. And so these would be the individual velocities that are being pulled relative to no velocity, right? So static observer, this is the velocity of the Earth relative to that static observer. This is the elevation, and this would be velocity. So that's the reason that it moves in different directions. If you ever see on the TV, people, I remember seeing a TV program on the equator of someone taking a bucket of water and pouring it like the drain going down, and then moving it to the other side of the equator, 10 feet, and showing that it goes the opposite direction. Well, it won't, because it needs to have a large span for the differences in these velocities to be different. Of course, the other reason that you don't get these things at the poles, if you had something going around at the poles, there's no differential velocity from one side to the other around the pole, right? So you get these storms. I presume the reason you get them in the mid-latitudes is because the difference between the velocities are so large. The other thing that you can do now with fluid mechanics relative to the storm surge is that we know that if you look at a storm, then I think the deepest storms you can get at the outside would be 1 bar, and the center would be 900 millibars. So this is 100 millibars different. So this is 100 millibars is 100 kPa over 10. This 1,000 millibars is a bar, right? So this is 10 kPa. And so if you think about the storm surge, if I can draw it, what it would look like, you could ask yourself the question, is a 13-foot storm surge, which is about almost 4 meters, actually probably closer to 3, 10 feet would be 3 meters, is that just due to the difference in pressures? So this would be 1,000 kPa, 100 kPa rather out here. This would be 900 kPa here. And so you can use your manometer equation, right, to write the difference between P1 and P2. And it would just be that P2 to this point here, H, P2 minus H gamma, water, is equal to P1. And if you put in, so you get P1 minus P2 equals minus H gamma W. And so you can calculate exactly what H would be, and you know that the difference between these is 10 kPa. Gamma W is 10 kilonewtons per meter cubed, and so the ratio of these is 1 meter. So you can tell exactly that the storm surge is not due to the air pressure alone. It has to dome, the sea would have to dome up in here to be able to satisfy our manometer equation. And so you know that this kind of magnitude isn't due to that. And I guess what it is due to, the fact is that if you look at a shoreline that goes through here, with this being the shoreline, this is being driven here. The storm surge is always larger in the onshore windward part and is smaller in the offshore windward part. So the storm surge would be large here and would be less here. And so this extra, the difference between 1 meter and 4 meters, the 3 meters, would be really the water being pushed up, actually being dragged along by the circulation of the air above it as it circulates here and being pushed up against the beach. And I guess I was always surprised to learn that counter to conventional wisdom, most of the deaths in hurricanes are freshwater drownings. It's not people getting washed out to sea and drowned in the sea, but it's people driving through streams or being trapped in basements, etc., or not being able to get out of it. There's a cheery note. So anyway, so something about the natural world. We finally got a hurricane. Not such great news for people in Jamaica or Cuba last night, but nonetheless. Okay. So anyway, some interesting things we could do. So let's go back to what we were going to talk about today. So I'm going to talk about the energy equation. The energy equation includes frictional losses, as we know, and then we'll use those ultimately to define Moody charts, which are kind of the essence of how we deal with pipe flow, which is a chart that looks like this. You might have seen it elsewhere. So let's talk about the energy equation. It's week 8, right? See if I can write well. And so we could draw a little simple diagram to look at flows between different portions. 2 buckets here, right? And we have an upstream and a downstream. And we could, I guess, I'm getting very fancy here. Could draw a datum on this. And we know that our energy equation, the one that we'll use, the Bernoulli-like one, not the one with entropy in it. I know you have thermo today on your minds. And that is what? We need to write it from upstream to downstream, so it is Z1 plus pressure head plus velocity head plus pump head equals the same downstream. Plus velocity head squared over 2g plus the sum of major losses and the sum of minor losses. So in our parlance, major losses would be losses which are small incrementally, but over long pipes are large. And minor losses would be things like, flow in bends. If you imagine flowing down here, just as a little pictorial view. We know from this that the pump head is equal to the power, watts, divided by unit weight times volumetric flow rate. So this is also mass flow rate. So this is not to be confused with our relative velocity, right? Uppercase W. It's the same as mass flow rate times G. That's just the same as this. It's positive if it's a pump. It's negative if it's a turbine. And so what we could do with this equation, or this situation, is we could write Bernoulli upstream and downstream. So points 1 and 2, or the energy equation. And if we do that, bless you, we know that P1 is equal to 0 if it's atmospheric. We know that V1 is equal to 0 because it's a big tank assumption. We know that P2 is atmospheric, and we know that V2 is also 0 because of the big tank assumption. And so if we substitute it into this equation, I won't write it out, for 1 and 2, then what we get is, what are we going to get? We're going to end up with an elevation term, which would be this, I guess. And this would be this. But nothing else. No pressure, no velocity, no pump in the system, and we have to have this. And so it would be something, well, it wouldn't be something, it'd be Z1 minus Z2 is equal to the sum of HL. Let's just amalgamate these. And so the point here, worth noting, is that this is really the energy grade line in our system, what we talked about before. And this, by definition here, is the head loss. So graphically, that's exactly what it is. This is just Bernoulli equation between upstream and downstream. The only term we have is elevation, head, because there's no pressure, no velocity, and we have this. And so this is the equation. So if it's Bernoulli, without these terms on the right-hand side, that's an unsustainable system. So the only reason this way this can work is that there is some pipe loss of energy dragging on this with some shear stress acting through Newton's law, that tau is equal to mu dv dx or y. Be dv dr, I think, is what it would be. You could also write the energy equation between two other places. You could write it between here and here. So this would be 3 and 4, in which case this would be Z3, and this would be P3 over gamma. And likewise here. Perhaps I don't need to do that. It's getting a bit busy. This would be written inside the tank, so I shouldn't really draw it in the pipe, right? It has to be the static head in the tank, so which would not be that, right? It would be this. P4 over gamma. And so if we wrote the equations between 3 to 4, then no longer do we have zero pressure at this point. No longer do we have we don't have zero elevation head, but we do have the fact that V3 equals V4, right? If the pipe diameter doesn't change, cross-sectional area doesn't change, so within the pipe, the velocities as we go into it have to be the same, and so the magnitudes here are that. And so if that's the case, then we'd have Z1 plus P1 over gamma minus C2 plus P2 over gamma equals sum of heads. I've incorrectly labeled those, right? This isn't 1 and 2. It has to be 3 and 4. This is 3. This is 3. This is 4. And this is 4. And of course, Z3 and Z4 are the same. So these drop out. And the bottom line is that P3 minus P4 over gamma over unit weight is equal to HL. Exactly the same expression as this, just written in a different way. So if we choose our locations differently, then we end up with a different magnitude. And so in other words, in this, we get the magnitude of the pressure drop along the system divided by unit weight is this. And so you could also think of this as a pipe, as we will do. And with some pressure dP acting up here, dropping along the length. I think if you've looked at the videos already, you'd have seen this kind of analysis, I think, in maybe Monday's. A length. I guess we might have on here some roughness, which we'll call epsilon, which is the absolute roughness. We have a diameter, which we'll call d. We'll have a flow velocity out of the system, which we'll call v bar, I suppose, just to make the case that we're not looking at we said that the distribution of flow should be kind of parabolic, but actually we won't consider that. We'll consider it as an average velocity, which is across the whole width, which would just be v bar. And I guess in this pipe we'd have fluid flowing at some density, it would have some viscosity, and a pressure drop. Are those the only parameters we need? I think so. And so what we could do is, if we wanted to define exactly what's going on, we could define this behavior in terms of dimensional analysis. So dimensional analysis means that we don't have to have a relationship which describes what's going on. So it's a very powerful method. It's kind of interesting, it's called dimensional analysis, but it works with dimensionless numbers. And it merely says that if you have, I'm not sure what we used, n quantities, and in this case our n quantities are dP, density, viscosity, velocity, length, diameter, and roughness. So these are all lengths. So these are uppercase L. And we have, I'm not sure whether you used N and K units, which are mass, length, time, and in the book they use theta for temperature. We won't use that. And it could also be radians per second, which is 1 over seconds. Then you can calculate how many dimensionless parameters you have based on a number of so-called pi groups equals n minus k. And so in this, we have density, and so kilograms per meter cubed is equal to mass length minus 3, etc. So we have mass represented, we have length represented, we have time. This is meters per second, which would be in units is length t minus 1. And so we have this represented, no temperature. So for our particular case, we have 1, 2, 3, 4, 5, 6, 7 parameters. And we have 3 groups defined, and these represent 4 pi groups. And you can use Buckingham pi to be able to define them. We won't do that today. You can have a look at, there's a formalism to do that, and it's a recipe. But we could look at grouping these together, and you can do it by inspection as well if you know what the answer is. It's kind of cheating, but let's do that here. So we have 4 dimensionless parameters. Not very good writing again. And so we could write these, and I'll write them in shorthand as an Euler number is a function of Reynolds number, length over diameter, and roughness divided by diameter as well. Could be roughness over length, and these aren't unique. So you can see immediately from this that if you define these, the Euler number we defined on the, well, I wasn't here for the second time we met, but in the video for E 1.2, the Euler number is a pressure divided by a density and velocity squared. A Reynolds number is given by a velocity, a density, a characteristic dimension, and a viscosity. If you work out the units on this, you'll find out that there are no units. M0, m to the power 0, L to the power 0, t to the power 0. And obviously these are length over length and length over length. So these are the 4 parameters. And so what dimensional analysis says is that if you can define some non-dimensional parameters which describe your system, and we haven't done anything, we haven't solved any differential equations, we've just put these together from an assembly of the quantities that we think would control the system, and we could guess what the link would be. And so dimensional analysis merely says that we seek similitude. And this is all in the movies for last similitude, yeah. So similitude requires that one, we have dimensional similitude. Similitude. And that is that length over diameter for the model equals length over diameter for the prototype. Pipes are kind of boring, but it means that if you used a piece of pipe which was a centimeter in diameter and a meter long, and the prototype was going to be 10 centimeters in diameter, it had to be 10 meters long to be that. And so the easiest way to think about that, and I think in the videos, you could think of an airplane as being the span of a wing as a length, and maybe the width of a wing as the diameter. Then if you want to have a prototype, then it would look like this. The scaling between those would have to be in the same scale. So this D prototype and this L prototype would have to be in the same proportion. So in other words, we're saying this. Actually, it's written above. Or it could be the other way around. It's a scale model. So if you're doing something in the wind tunnel, then the model you have to be has to be the same in all aspects and all dimensions, just to scale down. The second kind of similitude we want to get is kinematic. And so that means that that means that the Reynolds number for the model and the prototype have to be the same. So the velocity, the density of the fluid, the diameter, the characteristic dimension, and the viscosity of the model has to equal the velocity, density, and diameter of the prototype. And so if you're flowing in the same, it's a plane flowing in wind, then it's the viscosity of the air and the density of the air, viscosity of the air and the density of the air, which the plane flies in. And the scales of the model match up, and you have to choose a velocity relative to it. It's not necessarily the same velocity in the wind tunnel as would be in real life. And so the reason for doing that, I'm not sure that we've looked at it, but you can imagine, if you look at the Tacoma, actually, yes, yeah. You'll all have seen the Tacoma Narrows Bridge tear itself apart, right? In high school lessons. And so if you imagine that air is coming in, the reason it flew apart is because air at constant velocity was impinging on it, and it would flow above and below it. And the flow regime at very low velocities would look like this. So V low would look like this. Let's see how fancy I can be here. But if you increase the velocity of flow, then what you'd expect to happen would be at this downstream side, you'd get vortices forming. And these would cause what's called actually a von Karman vortex street, as in a road. And the idea is that when each of these sheds from either the top or the bottom of the box girder, it pings it, like pinging a guitar string. And if it pings it at just the right frequency, the characteristic frequency of this long span, then it will make it vibrate, and that vibration will slowly build until it becomes galloping gurdy. And so this is at a fast velocity. And so this would be at a Reynolds number which is low, and this would be at a Reynolds number which is high. So what kinematic similitude is saying is that the flow regime around the bridge has to be equal in the model and the prototype. So if it's behaving like this in the prototype, you'd have to have a model that was flowing at an equivalent Reynolds number, because then the flow regime would look like this. And then the third part is so-called dynamic similitude. Similitude, too lazy to write it. And that is that the Euler numbers match up. So this is RE model equals RE prototype. This is that EU model equals EU prototype. And that is, if you write it out in longhand, the pressure, that's pressure, not density. Pressure divided by density V squared for the model equals the pressure divided by density times velocity squared in the prototype. And if you think about it, we've done something like this, right? Sitting on San Francisco apron, our truck, and this is our jet engine. The force that's applied to this is due to the pressure that's applied to it. And so we have a pressure that's distributed over the side of this truck, which we could calculate from the V squared over 2G term just by using Bernoulli. And that dynamic force that acts on the truck, if this is a pressure, then the force is actually uppercase P, right? Just the sum of this times the area. pressure, not density. And so this says that the forces that are acting on the structure will be the same. So if you satisfy dimensional similitude, you have a scale model. If you run the model in the same flow regime in the wind tunnel, it will represent the plane flying in flight. And if you satisfy both of these two, then the pressures that are applied on the model, which you could measure by the lift anchoring the model down in the wind tunnel, would be the same as the lift you'd get from the plane at the real size. And you haven't solved any differential equations here. We've just done this purely by looking at a model in a wind tunnel. And so it's an incredibly powerful way to be able to do the minimum number of experiments, not just in fluid mechanics, but in all branches of engineering. So cool. I think dimensional analysis is kind of a cool thing. So that's 3 days of dimensional analysis kind of wrapped up into the very essence. And I guess the way of thinking about it would be this. If you think about plotting, and I guess this is what we'll do, is if you plot the Reynolds number, which is equal to velocity, density, characteristic dimension divided by viscosity, and you plot the Euler number, which is equal to the pressure on the structure divided by the density and the velocity of the fluid flowing over it. So these would be the velocities. This would be the velocity here. I guess it'd be the far field velocity, right, coming in. And so the idea is if you run your model at a given Reynolds number, so say it's flow in a pipe, which we'll look at, or say it's flow over the bridge. So you run your model at a specific Reynolds number, then you can measure the pressure that occurs on that model. So this is the model, and this is the model. So you run the model, you choose a velocity to flow over it, so you can calculate what the Reynolds number, because you know all these other parameters. You can measure the pressures that are applied on your model, and therefore you can plot the Euler number from that. And then you know that if you are running then the prototype at the same Reynolds number, then the Euler number has to be the same for the prototype. So now if you have the magnitude for the Reynolds number, you can come over here and you can calculate this. So if the requirements are L over D model equals L over D prototype, RE model equals RE prototype. So if you satisfy these, then EU model equals EU prototype. And so this is just a pictorial representation of that, is that if you have the right flow regime, by definition, the pressures will be replicated in that same model. And so I guess in some respects, you could think of these 2 pi groups as defining the system. We have actually 4 pi groups potentially for our pipe. We have 2 length size ones. So you could imagine that there could be different values of, say, epsilon over d. And so if your model actually had this epsilon over d equals 1, it wouldn't be 1, I guess it would be 0.01. And this could be epsilon over d equals 0.001. Then you potentially have different numbers. So if you only have 2 variables, this is absolutely true and they'd meet at a point. If you had a third variable, you'd have to do it also at the same magnitude of similitude for that variable as well to be true to form. So this is really what it means. And so I guess perhaps we won't have time to do this. Yeah, actually perhaps we do. So what we could do is we could do this for our pipe. And so if we do an Euler number, which is equal to pressure divided by density v squared, and we plot Reynolds number as being equal to velocity, density, characteristic dimension, and viscosity. And say we do an experiment where we take our pipe And we have a value of length, we have a value of diameter, we have a value of roughness, which we keep constant. We put a pressure upstream and downstream. And we measure a velocity that comes out of the pipe. So it's the average velocity that's a constant across the section. So what we could do for dP1 is we could calculate an Euler number 1 would be equal to dP1 over rho v squared 1. And a Reynolds number, which would be velocity 1, density, diameter, and viscosity. So the only parameters that are going to be changing will be pressure and velocity. And so we could calculate an Euler number for this, and it would give us an Euler number, and it would give us a Reynolds number, and a single point on that diagram for number 1. So we could then in the lab do the same experiment, but we could add an extra pressure. So this would be dP1, and so this total amount would be dP2. So dP2 equals 2 times dP1. And you can imagine, if you fill this up, we know from Darcy's law, right? If it's filled with sand, if you doubled the pressure gradient you apply, the flow rate is directly proportional to that. So the velocity would be double. And so if this is the case, so for 2 dP1, V2 might be equal to 2 times V1. And so if we calculated the Euler number for this, the pressure's doubled, but the velocity's doubled. And so V2 squared in this would be 2, and this would be 4 in the bottom, right? So this would be the magnitude. The magnitude of the Euler number here would be equal to 2. So this would be EU2, and this would be EU1. And if we calculated the Reynolds number for this, the velocity is doubling from the previous one, so the Reynolds number would increase to be this. Do it as a straight line, and this would be 2. So this would be Reynolds number 1, this would be Reynolds number 2. And as a result of that, we'd end up with a curve. We could do it for increasing it, and we could get some other values. It would turn out, if we did it for 3, which would be off this scale, we might expect that this would be a progression of this. So solved no equations, said nothing about differential equations. If we did 3, like what happened, if we did dP3, I guess this would be 3 times this. So this would go up to be 3 times this, but this would be 9. So it would go further down here. I won't complicate matters by doing that. And so just by doing experiments and plotting carefully in terms of dimensional similitude, we're keeping L over D and we're keeping epsilon over D constant. It's the same pipe. We're just changing the driving parameters of pressure and measuring the velocity. We get a graph that looks like this. And so we could surmise that in this case, and we've written out before, that epsilon is equal to some function. Actually, let me draw uppercase F of Reynolds number, length over diameter, and relative roughness. And what we've just done is we've made the beginnings of a Moody chart. So this is a log-log scale. The Euler number, or the Reynolds number, is equal to what we'll call friction factor. We'll find out, we're getting a bit long in the tooth here, that the head loss that we talked about here, if I just scoot back, that we'd like to determine for a pipe is actually given by an expression which is a friction factor, length over diameter, and V squared over 2G. kind of an Euler number if we manipulate it in some way. And so all we're doing is we're saying that we can calculate what this friction factor is if we know these other things by doing experiments in the lab. And that's exactly how these charts were originated. And so this straight line here is this curve here. You have this in your notes. If I scroll down, this is exactly it, right? You have this in your notes. And so this is exactly that curve that we just talked about. So this is for flow within a pipe, and perhaps we'll talk about it next time. I guess we're right up against the wall. This is the head loss is equal to a friction factor, length over diameter times v squared over 2g. And we can define a bunch of two regimes. An important number on this is 2,000, which is 2 times 10 to the 3. And so this is laminar, in which case flow within our pipe would be actually flow within our pipe would look like this parabolic distribution, which we haven't quite got round to talking about, the velocity. And this is turbulent. Well, I guess this is turbulent. And so within our pipe, the velocity for this distribution would just be a box, square. And actually, the easiest way to see it would be kind of like a golf ball. So if you imagine a golf ball or a sphere flying through the sky, this flow regime around here would look like this. And the flow regime the other side of this would look like this. These vortices. And so what we're doing is we're satisfying by the Reynolds number at the bottom here that the flow regime we have is appropriate. And so that defines the behavior. So the behavior we've looked at so far with this really simple illustration where we double the flow velocities, we double the pressure drop, is in the laminar regime. And it doesn't really hold as we get to higher velocities. And we see a couple of interesting things. And that is that this friction factor is a function of Reynolds number and relative roughness. And if I make a copy of that, which I will do, this is the last equation I'll write today. Might have been easier for me to write it, actually. I didn't want it. Easier to write it, indeed. The only point I was going to finally make is that in the laminar regime, the friction factor is a function of Reynolds number, but it's not a function of relative roughness. In the turbulent regime, the friction factor is, in terms of this, is same equation, is a function of Reynolds number, but it's not a function, not a function of Reynolds number, but it's a function of relative roughness. You can see that because these lines are horizontal. So the friction factor as you go across here doesn't vary with Reynolds number, because once you get to this threshold, it stays constant. And so we'll use this observation to be able to actually compose this chart maybe next time. I guess we went in a different direction. Okay, that's all I wanted to say today. Next time we'll continue trying to use these things. Perhaps we'll use it on the jet lev as an example, where we take this equation for the energy equation, which is all this, this term here, and use it for an example, which is the jet lev.